Almost there, folks. Hey, it's official. Looks like we can start. Welcome back, everyone. So we're closing out week 7, meaning next week is midterms week. So almost at the halfway mark. Congratulations, everyone. Any questions at all to start us out today, folks? Okay, well, just for a quick rundown of the announcements, nothing too major going on this week or next week, since next week is midterms, but we don't have an exam or any special assignment that week. Where we're at right now is we're finishing off section 3.3. Then we're going to be moving into the product rule and the quotient rules. As usual, I'm not going to try to rip through these and go as fast as possible, so we may not get to section 3.5, but it's available there early just in case you want to take a quick early look at that section. Also, we have our third quiz coming in due today, and the quiz number 4 is the new quiz that's posted. Quiz number 4 is heavily based off what's going on in section 3.3, and so it's a good preview of what exam questions would really look like coming out of that section. Well, any questions or comments at the moment, folks, with any of the announcements or anything else otherwise? Okay, let's get started then. So in section 3.3, looks like the due date for this one is going to be October 9th. And where we left off on was we did a lot of differentiation problems. Let's take a preview of these before we get started. But the big punchline to many of the problems that we're doing here is a lot of them require additional algebraic steps. For example, if you see something like this problem, where you have anything in the denominator involving a variable x, we need to divide through, if possible, so that we can get our function in this form by the red dot. Once we're here, all of our differentiation techniques in section 3.3 will work. We don't want things that are being divided or multiplied like up here. We want things separated out by pluses and minuses. And at most, they'll be multiplied or divided by a constant. That's not going to affect our differentiation at all. So that's how a lot of these kind of problems go. And this one is just a couple extra exercises in that direction. I honestly think that these are kind of tricky ones. So let's first do some discussions on exponents for that thing there by the red dot, and then we'll go ahead and differentiate it. So one thing to notice is there is a lot of exponent rules that come up on this section, and that's the purpose of the review notes that you have right here on the Moodle website. So again, just to plug these notes once more, take a look at those, spend some time on them, and it makes everything in section 3.3, 3.4, 3.5 a lot easier to breeze through. So first thing that's going on with exponent laws is if you see e to the power w plus 1, we can use this exponent law right here. The exponent law goes, let's make it more generic, a base a, so a for anything, to the power of m plus 1 is the same thing as a to the power of m times a to the power 1, which would then become a times a to the power of m. So the reason this rule works right here is if you're in this situation, you add up the exponents. But what we actually want to do is break up the exponents on that thing. Reason being is we have a formula that goes like this. The derivative with respect to x, this is up there in the notes at the very top of the document, so we'll just put it here so we're not scrolling up and down. The derivative with respect to x of e to the power of x is e to the power of x. So that's the formula that we have to use right here. But it doesn't fit with that function. In order to use the formula, it could be e power w. The variable itself is immaterial, but it had to be exactly w to use that formula. So our very first step on this is we take the function, dependent variable z, like the variable y, take e to the power w plus 1 and break it down as e times e to the power of w, and then just copy plus w. So that's our big technique that certainly makes this question right here an extra tricky question, I'd say. Not a good candidate for an exam question, but a potential homework question. That's our very first step we would take. Any questions at all, folks, with that first step? Okay, where it stands right here, this is still a tricky problem. So sometimes when you have things like this, where there is just a whole bunch of different symbols, notice there's no numbers on this line whatsoever. The numbers have just completely vanished. But think of your z by analogy. We're differentiating something like a y, where z would have been. Working with the analogy, that's a constant, but it's a weird one. E is approximately 2.71, but the constants we're used to seeing is something like 5. We definitely want to copy the exponential. Let's call it e to the x plus. Notice that instead of x, instead of the w by the red dot, I'm visualizing it as an x just to work with the analogy further. So that will be plus x as well. So differentiating this question or this function in black is tricky. Lots of different symbols that we're not used to seeing. But if you can think in terms of what we usually do, you're solving a problem that looks about like this. So over here by the red dot, it's a little bit easier. Y prime would have been, first, that's a constant multiplying the exponential. So it'd be 5 times the derivative of e to the x, which is just e to the x by the formula right above. Then we differentiate plus x. That turns into just a plus 1. That's not the answer over here, but it helps us think about how to get this answer. Any questions down here, folks, with that analogy derivative? Okay, well, keep this in your mind's eye as we differentiate this one. We'll say that z prime, if you prefer Leibniz notation, you might wrote dz dw, but we'll just go with the z prime on this one. We're trying to give the notations their equal fair share. So z prime will be, first, that's a constant multiplying a function. So the constant e copies in. Differentiate e to the power of w, and you get times e power w. Then differentiate w, and we get a plus 1. Again, pretty much what we did right here, but this was just a special function to help us visualize that result. So that's what the derivative would be for the function z equals e power w plus 1 plus w. Kind of a strange function. Any questions at the moment, folks, with part F?
I have a question.
Yeah.
Why doesn't the first e go to 0?
Oh, that's a great question. It's all about that multiplication you see right there by the red dot. So let's do a slightly different problem. Suppose we had z equals e plus e to the w plus w. Then I think this is the kind of function you're thinking about with that question. If we differentiate this function, then the e right there by the red dot is a constant, and it's not multiplying. So the constant multiple rule doesn't factor into this problem. We would get 0, or first let me write z prime so we know what we're calculating. We would get 0 plus e to the power of w plus 1. So the heart of that question there, it's all about the fact that it's multiplying right there. Does that make sense with that question there, Jamie?
Yes, and then if the exponent is a variable, do we always keep it the same when we differentiate it?
Almost always. It turns
Okay.
out it's not completely always going to be the case, but if you have something that looks like this, derivative with respect to x, or if you're writing it out in Leibniz, or excuse me, prime notation, if it's e to the power of x differentiated, you always get just e to the power of x. But we're going to discover a new formula that goes like this. If it's maybe something like 5 to the power of x, we've changed the base e, which is a common base because it makes the calculus a little bit easier, to just something else. Derivative on that one would be 5 to the x, so it starts out just like this one down here, but there's an extra multiplying factor. We have to multiply by the natural logarithm of 5. Again, we haven't quite gotten to that formula there, but that's the formula that's coming up down the line. Other questions about that so far? Okay, those are lots of great questions. And again, it's a pretty oddball function that we differentiate on this one. So I think the worst thing about it was the w power plus 1. That's not something that's going to be a typical exam question, but if it ever comes up in the homework, this is the strategy down here. Well, we have one last question on the notes. Then we're going to take a look at section 3.4 with the product rule and quotient rule. But first, we need to differentiate this one last function. Any volunteers for what that derivative would come out as? I'm going to load a calculator while we're thinking about it. Okay, so just like part F, that was a pretty tricky problem. I'd say part G is actually worse. When you see this kind of problem, one thing that you want to really resist the urge to do is allow the power 8 to come down and multiply and reduce the power by 1. Reason that won't work here is this is not a power function. That kind of strategy would only work if you had the variable x right exactly where the E symbol is. If you had, for example, let's just write that problem down just so we can visualize it. If the problem was y equals 3 x to the power of 8, then the derivative dy dx would be 8 comes down and multiplies a 3 for a 24. New power of x is 1 less, so now it's power 7. But that whole strategy breaks down here by the red dot. Anyone see what the issue is with that function there? And if you're not sure, no worries. I'd say this one is, again, the trickiest problem in the whole set, more tricky than part F. But the idea with this one is it's abstract simply because we have a base E, which is truly a number, but now it looks like a variable or some other symbol. If you plug that in your calculator, however, you would go y equals 3 e to the power 8. And this is what the calculator spits out. 3 times e to the power of 8 is just shy of a constant, right under 9,000. But the big takeaway is it's constant. And we know the derivative of a constant, that really weird one over there in part G, is always 0. So watch out for these kinds of things. I'd say F is not really a fair exam question because it requires just abnormal exponent surgery. But this one is going to be. We have to always watch out for strange constants like this one. So the quick answer on this problem, even though it's a tricky one, is that y prime equals 0, since 3 e to the power of 8 is a constant. Let's put here, it's approximately, just for our own knowledge on that one, 8942.9 upon rounding. Well, we did it, folks. This is differentiation using the basic differentiation laws in section 3.3. This is a good section to come back to, especially when you're reviewing for exam 2 or the final exam, just to run through these problems again, get some extra practice on how they go, because sections 3.3, 3.4, 3.5, they're going to come up all the time in this course, all over the place. Any last questions or comments then, folks, before we close out the notes? Okay, so let's close this out. And now we are in section 3.4, the product and the quotient rules. Let me move this window over. I have my thumb drive here on the right. So 3.4. It starts off with a formula and then a big warning right out of the gate. And that's appropriate since one thing that we mentioned in section 3.3 is a lot of functions do not require the product rule. Like this one over here. This is a case where the product rule should not be used whatsoever. However, over here, the one in green, that's a situation where we must use the product rule. So part of our goal in section 3.4, when it comes to the product and the quotient rules, is also to kind of train our eye to decide when is the right time to use it. Since if we treat every single problem like this one as a product rule problem, we're actually taking a lot of extra steps that are really needless steps. Simple algebra can sometimes make this a very simple problem. Well, let's take a look at how it goes. Stated in Leibniz notation, it would say if you're differentiating a product, a product means f of x times g of x, written this way, just putting them together. What you would do is you get two terms actually, which is a bit of a surprise. This was discovered by Leibniz. You take the function f of x and multiply by the derivative. So that's g prime of x, or in Leibniz notation, d by dx of g of x. Then you copy the g function and differentiate the f function. There's a lot of different ways to write this. So usually when I write my derivative with the product rule, I go in this route. Let's use a little bit of color coding to express it. The function f of x, I differentiate here, and the function g of x, we just copy. Really, that's what's being said on that term. That's the derivative there, and that's the function being copied. Then you make another term, so separate by plus, where you copy the opposite function. So here's f of x copied, and then finally differentiate the g function. So let's use color coding again. That function gets differentiated, and that's what's being expressed down here as well in the Leibniz notation. So either way we visualize it, this is the result of the product rule. It's just a matter of write down f of x times g of x twice, and then put a prime symbol on one, and then the other. That's the essence of the product rule. Any questions, folks, with this statement, either in prime notation or in Leibniz? Okay, let's give it a try right away. Let's do the one where the product rule should be used. And you know what? The word should is okay here, but let's make this a little bit better. Let's use the word must. Must is a strong word in mathematics, and it's the right word here. I don't have any other way to do this one unless we really use the product rule. So here's how the product rule would go on that one. One thing that's unfortunate is sometimes our functions are indicated as a g of x, which looks like a conflict in notation if there's a g of x in that function already. But really the names f of x and g of x, they're immaterial in a really strong way. What is more important is the pattern. So I would always start this off by going like this. G prime, let's make that a more convincing prime symbol, there we go, equals, where the red dot is, we differentiate something, we move over and we just multiply by something. Then we go plus, we multiply by something here, not differentiated, so there's no prime symbol. Then finally over here, we multiply by a derivative. So we'll put a prime symbol on that one. Next, think of f of x as just the first function and g of x as the second function. So down here, x cubed is our first function. It goes into the first slots. It gets differentiated over here. And then over here, it's just copied in. Any questions to that stage? Okay, then with the second function, g of x, it gets copied in over here, differentiated over here. But if we just started by putting down the pattern, essentially 4 parentheses separated by addition, a prime symbol on one, prime symbol on the other, all you're really doing is writing x cubed e to the x twice and just dropping into those little placeholders that we put in with parentheses. So e to the x would go here and here. This is not the end step, but this is really good progress. All we need to do is take that derivative there, and we'll have our total answer. So in the next step, derivative of x cubed turns into 3x squared. It's still multiplying e to the x, but that's just a copy. So copy down times e to the x. Then go plus. Over here, x cubed is copied. We didn't put a prime symbol on it, so we'll go plus x cubed. Then we multiply by the derivative of e to the x, but that's the world's best derivative. That turns into just e to the x. And that's our result right there. That's the derivative of x cubed times e to the x. Because this is a product of two functions, and the product rule has two terms, we expect two different terms on a result like we see there. There's other things you might be able to do to this if you wanted to. For example, you could factor out e to the x. You could factor out the least common, or excuse me, the greatest common factor, x squared times e to the x. But for a lot of these problems, if we're not doing anything further with the function, this is normally a pretty good stopping point. Any questions at all, folks, on that conclusion there? Okay, so this is essentially the product rule. It's always this kind of pattern. And when we're learning it for the first time, I'll often do this strategy of just writing down the 4 parentheses and moving the prime symbols around. Jamie says, will these be given to us on the exam, or should we start memorizing the formulas? These would be formulas where it's a really good idea to start memorizing, but also keep in mind on exams, I do provide some formulas. So I'm going to make a note just to be really more explicit about what's on the exam, what we have to memorize. So let me make a note here to provide formulas early. I'll try to get working on that right away. And I would say for these kinds of problems, let me go back here. I would provide some of these formulas. It would look about like this. On the real exam, once I get that sheet put up, I'm going to try to work on that soon, I would give this table right here of differentiation formulas. So you would know that you have the product rule right here, the quotient rule. You also have the constant multiple rule, derivative of a constant being 0. This one gets a ton of use, the power rule, and other great stuff like derivative of the exponent. So I'd say it's a really good idea to have them memorized so you don't have to look them up each time. But on a real exam situation, if you just forgot, then this will be here to help us out. Other questions about that so far? Okay, well, we did a product rule on this function right here using this pattern. Let me just zoom out a touch so we can see it all. Well, my window here for Zoom is not minimizing. There it goes. So using this product rule here, this is a case where we have no other recourse. We just have to use a product rule. And you can use a product rule on this one, but like we said before, it just forces you to take a lot of additional steps, which really aren't necessary. We explained a little bit of this when we were doing the notes in section 3.3. So the strategy on this one, the best strategy, the strategy of least resistance, least amount of work, is to just FOIL out the function. So we start by writing f of x. Once I get the pen working, there we go. Because we haven't differentiated anything so far. Come over here, distribute x into the group to the right, and we get 2x squared minus x. Likewise, distribute 3 into the group to the right to get plus 6x minus 3. Then that would tell us the f of x is 2x squared plus 5x minus 3. So essentially all we're doing is a little bit of algebra, but this is the algebra that we do all the time, that we know, that we love, the FOIL method. We exchanged a function that is not convenient to differentiate with one that totally is. That f of x is wonderful. It doesn't require any special formulas. It's now a section 3.3 problem. So let's write out the derivative. This time we are saying f prime of x since we're differentiating. Any volunteers for what the derivative should be for this function there? How about for that first term by the red dot? Anyone see what the derivative should be for that very first term? Absolutely, Jamie. So for the first term, 2 comes down, multiplies that 2. So the power, where the coefficient rather, is now 4. The power goes down to a 1, so now it's just a 4x. And likewise, same pattern on this one, because we have pluses and minuses separating the terms, no product rule any longer. The constant multiplying 5x upon differentiating gives us just the constant 5. At the negative 3, that's a constant without a variable, So the derivative of that constant, -3, just goes to a 0, and that's our total derivative. F prime is 4x plus 5, and no crazy formulas like above. This is definitely the strategy. Try to use the method that requires the least amount of algebra, the least amount of steps, and you're just going to be more accurate and you'll move through problems faster as well. So this is a good page to come back to, just as a reminder. Sometimes you do not want the product rule. Other times, this is a case where we must have it. With the notes below, we'll practice a product rule a little bit more, and then we'll move over to quotient rule. Any questions or comments whatsoever, folks, to this stage? Okay, let me zoom in just a little bit more here. Let's move down to what the typical problems would look like. So these are problems that you might see in this web assigned for this section 3.4. And the thing to note right away is some of them look a little bit odd, like this one, and others look a little bit more routine, like the 9t cubed e to the t. This one is a real challenge to differentiate. So part A is going to take us a little bit of time to get through, but part B is going to be a little bit more routine. Trouble with part A is we have x's in the denominator, so we can't use a power rule. We need to correct those x's down below. And this one's in radical notation. That's even worse. So let's write down our exponent laws we're about to use. One law says 1 over a to the power of n. That's our situation with those two denominators here and here. This can convert to a to the power of negative n. Then we can use a power rule on that term there. Other strategy is if we have something that goes like this. Let's write a generic formula. The nth root of a to the power of m is a to the power of m divided by n. The takeaway with this formula is whatever your index is, gives the value in the denominator. If there's no power m here, like our x, it's not x squared or x cubed inside the fourth root, then the formula just reduces to this. Nth root of a equals a to the power 1 over n. So this looks like it's going to turn into one of those problems that involves lots of fractions, unfortunately, but we will methodically get through it step by step. Let's make sure we have enough space, though. So starting out, I'll just write a y because we haven't differentiated anything at the moment. We're just changing this algebraically. The 3 divided by x up here turns into 3x to the power. Well, it didn't display the exponent in that denominator, but the denominator is known to have exponent 1 if you just write it x. So if it's power 1 here, we move it up to the numerator, and it'll be power -1. This one's a little bit easier because it's displaying a power of 3. What would happen here by the red dot is we go plus 5. X is now in the numerator, so that power, which was positive 3, is now -3. Finally, the last exponent surgery is a fourth root of x is just x to the power of 1/4. Then -1 just copied in, and that's our function. Any questions, folks, with what we did with the exponents? Okay, now seeing how this function ended up, we would call this one a problem where the product rule is not needed. Reason for that is if we expand this out by FOILing, we'll take 3x-1 multiplied by x power 4th, but we can combine those x's into just one x, 3 to the power, 3 times x to the sum power. We can't ever do that with this, t cubed times e to the power of t. There's no way to separate that out. So that's a function where we have to use product rule no matter what. So this one's kind of a review problem, and this will happen in our notes in section 3.4 in our homework assignment. We have to judge if we really need the product rule or if there's an easier alternative. This turns out to be the easier alternative. What we're going to do next is boil out the groups like we did on the problem above and just differentiate term by term. Let's write this out carefully since we do have a lot of exponent work to do still. Multiplying here to here gives us 3. And let me make this go down just a bit so we can fit it all in. y is going to be equal to 3 x power of negative 1 times x power of fourth. I will simplify that one carefully. Last time we did this in the class notes, I think we just ripped through it kind of fast. Sorry about that. With exponents that are fractional, it's worth taking the extra time on that thing. So we'll do that in the next step. Next, we multiply here to here. So that's negative 1 times 3x power negative 1 for altogether negative 3x power negative 1. That finishes those multiplications. So next, multiply here to here. That's going to be plus 5x power negative 3 times x power 1/4. And our final multiplication is minus 5 x to the power negative 3. So far, all we've done on this step by the red dot was we made our exponents more easily differentiated. Then on this step, we FOILed, but now we have to do a couple things. We need to combine the bases where the orange brackets are. So that's going to involve a little bit more fraction work with exponents. And the exponent law we're using is a to the power of n times a to the power of m is a to the power of n plus m. The thing that's critical is that you're multiplying your bases like we are here and over here. And this rule works for any n and any m. They can be positive, negative, they can be integers or fractions like we have here. Any questions, folks, before we go to simplify those like bases? Okay, well, the next strategy is, because we have to add the exponent 1/4 and negative 1, we want to take this one and write it in with a denominator 4. So let me put in just a little scratch work in this orange pen to say where that bracket is. This turns into x power negative 4 divided by 4 times x power 1/4. Once we get into this configuration, we're kind of home free. We'll use this idea to just add up the exponents. So it's going to be negative 4/4 plus 1/4 gives us x to the power of negative 3/4. So that's how these two combine. Does that look right to folks on that step? Okay, well, that was so fun. We'll just do it all over again with these two. So same strategy. We have to add a fourth to negative 3. That means we take the negative 3 and multiply by 4 divided by 4. So this will turn into 5 x to the power of negative 12/4. And then just double check. If you divide here, 4 goes into negative 12, negative 3 times, so we didn't change the exponent. Then it multiplies x power 1/4. Then the final step is we take negative 12/4, add 1/4, so we're at negative 11/4 altogether. It's 5x to the power negative 11/4. So now we have something to put here and something to put here. This next step is just writing this all in. So y, still not the derivative, just ordinary y. We have to resist the urge to put y prime on it until we actually differentiate. It's going to turn into, forgot to carry that 3 down. Let me put it over here just to make the notes more readable. The 3 is affected, and I just want to make it paralleled with this one where we brought the 5 down. So we get 3x power negative 3/4 on the first term. Next, we're over here, minus 3x power negative 1. On this one, we simplified and got plus 5x power negative 11/4. And finally, just copy on this one, minus 5 x to the power of negative 3. That's a lot of work to that step. Any questions, folks, so far? Okay, well, thanks for sticking it out with me on this one. Again, this one would be a really nasty exam problem. But when we do problems on the homework, sometimes there is a little bit extra challenging ones, and they're kind of mixed in the notes or mixed into the exercises. It's not always easier problems first and then harder problems later. So this is, in my opinion, one of the trickier, harder problems in the set to watch out for. If you see anything like this when you're working in WebAssign, this would be a great example to come back to in the notes, just to see some of the ideas and tricks you can use to get through it. Plus, don't ever hesitate to hit the Ask My Instructor button. I'll be very happy to help out with those questions. So now finally, all we've done is algebra. We haven't differentiated a single thing, but we took all those steps because product rule on that is a real nightmare. But now that we've done all that algebra, we can say the derivative of y with respect to x, so dy dx, or just y prime, equals the following. It's just the power rule and constant multiple rule over and over again. So over here, 3 is unaffected since it's multiplying. It gets multiplied by the old exponent, -3/4. And the new power of x, we always subtract 1. I think a cool way to visualize it, mentioned last class, was you're essentially just subtracting 4 from that numerator. Algebraically, you're subtracting 4 over 4, and so this becomes x to the power -7/4. Still a fraction, and that's 1 down. We still have to multiply that together, but we'll handle that on the next step. Then we just move down the line, 3 more to go. This one's not so bad. -1 multiplies -3. The new power of x is 1 less, so -1 minus 1. We're now at -2. And just keep on going in that strategy. Plus 5. It multiplies the old power, -11/4. For the new power of x, we're subtracting 4 over 4. That's the -1 part. So that turns into -15/4. So we're done with all the annoying fraction ones. This one's not so bad. First, we copy down -5. It gets multiplied by the old exponent, -3. The new exponent is 1 less, so now it's a -4. At this stage, we are basically there, but we still have to just simplify all these little multiplications that we see. Any questions at all, though, getting to this step? Okay, continuing to solve this out, let's just work out our constants and say the derivative is now -9/4, x to the power of -7/4. Like we mentioned before, I'm not too worried about negative exponents or giving an answer as positive exponents versus negative exponents, so you're fine to leave your answer just like that. Next one is going to be +3, x to the power of -2. Over here, -55/4, x to the power of -15/4. Then last one, +15, x to the power -4 rather. So it's a giant mess, but the function itself was a mess to begin with. And this is the result of taking all those steps. Any questions at all, folks, with the conclusion here? Okay, well, congratulations. In my opinion, I think this one is the hardest one for the day. And what made it hard was not the calculus. The calculus is basically everything in blue. That was just a couple lines. And the last line, if you just multiplied and got -9/4, you may have done this in just one step. It's all the stuff in the middle, the algebra, that makes it challenging, in my opinion. I agree with you. This would be a terrible exam question. If this really was on the exam, it might start off like this. I think this would be a better version for the exam. Say 3x plus 5x power -2, maybe x to the power 4 plus 1. I think that is a little bit more reasonable because, I mean, the exams are timed. We don't have the extra time to break things down like this. Well, other questions at the moment, folks? Questions or comments? Okay, well, we got through the hard one. Sorry, it's part A on there. I probably should have made that the maybe part C or something like that. But now our reward, though, is we get to do this one. This one is definitely not as bad. What makes it nice is the exponents we don't have to work on, and it's just an ordinary product rule type of problem. So working through this one, Color coding is not a bad idea when you're learning this kind of stuff. So I'm going to think of this as the first function and that one as the second function. So when we go to write out f prime of t, first, it's about the pattern. And even though there's going to be some formulas provided on exam 2, the more you're fluent with that pattern, the easier all this is going to be. So start off by putting down 2 parentheses, then another set of 2 parentheses. They're multiplying. Also, don't forget, you're differentiating stuff. So start with the prime symbol in the first slot. Let's highlight that just for extra emphasis. Then move your prime symbol over to the next placeholder slot. After you've done that, it's just a matter of copying. 9t cubed goes into the first positions. So we'll go here. That's where it's differentiated. And also goes here where it's just being copied in. Then move over to your second function, e to the t. It copies here and here. So the problems that are real product rule questions in this section, you might notice that e to the t comes up a lot. So that's probably sometimes a good giveaway, but it's not always a direct giveaway. Well, this is the very first step, and it's a nice quick step. Any questions at all, folks, with writing down this one line? Okay, although it's really great progress and there's not too much left to do, there's still a lot of stuff that we have to do to get credit. We still have to differentiate this thing and differentiate this thing. So here's what it's going to look like on our final line. The derivative of 9t cubed, well, that's just an ordinary constant multiplying a power function. Power 3 multiplies our 9, so it becomes a 27. And the new power of t is 2 for a t squared. Actually, I wanted to put that in blue just to convey that was the one differentiated. 27 t squared. Over here, this one gets copied, so I'll just put it in black to say we didn't do anything to it. E to the power of t plus, this one's copied, so 9t cubed. Then we differentiate e to the power of t. The best derivative in the world, I keep mentioning. Derivative of e power of t is itself e to the power of t. So that's finally our result. And again, some people like to factor their answer, and that's totally fine. In fact, that'd be a good idea in chapter 4. But since we don't have any further steps after finding the derivative, this is also a pretty good stopping point as well. How does that look to folks? Does that make sense on getting through that product rule? Any questions with it? Awesome. I'd say, again, when you're learning the product rule, this pattern right here is really the major key. The more you practice that and get used to it, the easier it is. And it's kind of like function notation. For example, if we had a function that was f of x equals 3x squared plus x, when you take the derivative using the definition of the derivative, you have to use f of x plus h. Let me let the pencil catch up. The pencil tool occasionally has a little bit of a lag that gets involved. Looks like it practically crashed these notes. I don't know if you can see this circle thing that's, or the word not responding up above. Let's give this a minute. Sorry, folks, I think I crashed my notes somehow. Yeah, it's really angry. I probably should be a little bit liberal with using the pencil tool. I didn't expect it to take down all of Microsoft Word. That is unusual. Well, give me a minute, folks. I need to figure out how to bring Microsoft Word back online. This is probably not the best use of class time, just staring at a crashing Microsoft Word document. Kind of embarrassing, but this is ISU technology, so it's not the world's most expensive laptop. I don't know if this is going to resolve on its own. Let's use Task Manager on this thing. And just to make sure the whole computer didn't crash, are you all able to still hear me in Zoom?
Yep, we hear you.
Okay, awesome. Thanks for letting me know. Appreciate it. Let me end this task here. Let's just reopen it and hope we didn't lose too much. Whenever we lose stuff, it's no big deal. I'll come back into the notes and write back in whatever we might have lost. Okay, we've got some recovery options. One at 1244 or 1244. That's not, 234. That's probably the one we want. Let me close that. Save this version and hey, we lost a little bit of this one. Again, I'm going to come back here and clean up the notes on this thing. If I forget to do that, let me know, since I don't want to leave you hanging on this problem. I'm going to have to come back to this one as well. I think we've finished off that derivative, but let's write it down just one more time, just so that's here on the notes again. F prime of t on this one was 27 t squared e to the t plus 9t cubed e to the t. And I'll put in the explanation here later. Sorry about the notes crashing. That's pretty weird. I'm going to maybe use this pencil tool a little bit more liberally. Well, weird crash. Sorry about that, folks, but let's move on to just the next problem. The problems didn't go away, thankfully. Let me put that down below. And here's our next function to work on. Now, this one's kind of an unusual one. Whoop, didn't mean to put away the participants window. Let me bring that back. There we go. This one's unusual because I'd say any start you make on this one is probably going to be just fine. You could FOIL it first, but if you did FOIL it first, there's still a product rule in this problem that you can't avoid, or you can just directly attack this one with the product rule. The reason this one is a product rule and we just can't avoid it is because you have to eventually take 2x times 4e to the x if you FOIL this. This would give us 8x. Oh, and I was just saying to be careful with the pencil tool. 8x e to the x. So when you get these two multiplied, that's your result. And that requires the product rule already. So I'd say for this one problem, it might be a good idea to just launch right into the product rule at the very beginning. So that's how we're going to handle this one. Again, what made this inevitably a product rule is because e to the x showed up. That's going to be kind of a pattern on these notes until we get some more functions with, let's say, logarithms. So again, strategy on this one looks like it's a good idea to just FOIL it out, or excuse me, hit it with a product rule right away. If we do that, think of 2x minus 9 as your first function, 4e to the x plus 1 as your second function, and here's how it goes. G prime of t equals, first it's the pattern, so a parenthesis with a prime on it. Don't forget your derivative. If you forget to put that on there, you might still get the right answer. But honestly, without that prime there, you might actually forget to differentiate and miss the problem. Here's a second parenthesis. There's always a plus in the product rule. That's kind of nice. P for product and P for plus. Two more parentheses, and the prime goes on the far one this time. Then put in your first function, 2x minus 9. It goes in both of the first parentheses. Then grab your second function, 4e to the x plus 1. It goes in just the remaining parentheses, the ones in the second positions. So it starts off with loads of writing things down and not quite differentiating, but this is a good first step. It will give you partial credit on an exam, even if we made a mistake on both of those derivatives. This is good partial credit. Well, any questions, folks, with this setup before we go to differentiate it? Okay, well, let's run through the derivative. Sometimes these derivatives can be kind of tricky, so let's make this one kind of a class derivative. Any volunteers for the derivative there by the red dot? What would that one turn into?
Is it just two?
Good call, Doug. That one turns into just 2. So lots of ways to think about it. You could think along the lines of that's a linear function with slope 2. It's in slope-intercept form. Or the derivative of 2x is exactly 2. The derivative of -9 goes to a 0, so it's just 2 in the end. Either way we visualize it. Good call. Then here, this is just a copy step by the red dot. Still needs parentheses though, so 4e⁻x plus 1. That factor of 2 now has to distribute through that whole group. And likewise, we need to keep parentheses on that group there. Still copying though, 2x minus 9. But from here, we do take a derivative. Any volunteers for this one? What would the whole answer turn into when you differentiate this? Oh, we got one through the chat. Good call, Cameron. This one just turns into 4e⁻x. I think this one is pretty tricky too, in my opinion. We had to know that the 4 is multiplying e⁻x so that we're dealing with the constant multiple rule. So when we differentiate, that 4 is unaffected. The e⁻x, its derivative is e⁻x, and the plus 1 turns into a 0. So just like Cameron said, whole thing right here in its derivative is just a 4e⁻x. So now we've got the derivative down. Any questions at all, folks, with where the work is at this stage? Okay. Now, one thing that is a little bit odd with how I did this one was we launched directly into the product rule. I still think that's a pretty good strategy for this problem. But now that we're on this step, there's a chance that if you gave WebAssign this answer, they may say it's not in a simplified form, that we need to do a little bit of extra algebra on it. And the reason for that is, if you have 4e⁻x here and 4e⁻x there, we have a real possibility for like terms on this problem. So we need to double check, multiply things out, and see if we can, in fact, combine things. So last steps is just algebra. If this was a real exam question, let's say out of 5 points, and you stopped right here, I wouldn't be too picky. But WebAssign wants us to do a little bit more, so this is the little bit more. Take the 2, distribute into this group. It's going to be 8 e⁻x plus 2. Plus, same thing on this one. We're distributing 4e⁻x, but we're doing it from the right-hand side. Big arrows helps with visualizing that one. It'll be 8x times e⁻x. And then here to here, that's -9 times 4e⁻x. So that would be -36 e⁻x. So let's analyze this a little bit further. As far as the like terms go, we have 8e⁻x, -36 e⁻x. But this one's an odd one out because it's just a constant. And this is the odd one out because it also involves the variable x. So just the underlined terms are like terms. And our total answer could be this. 8 minus 36 is going to give us -28 e⁻x's. Now I'm just copying plus 2, copying plus 8x e⁻x. Last step wasn't too bad, but it's tricky because there's lots of things to actually write down. The way I make a mistake on this is I forget to carry everything down. I might forget to copy the 2, for example, or perhaps the 8x e⁻x. I might just delete the x in my brain and forget to copy it down. So if there's ever extra algebra, just be methodical. Even if we're done with the derivative, you don't want to celebrate too early and miss the question at WebAssign because of a simple mistake. Well, any last questions or comments, folks, with the end on part C? Okay, well, that's the essence of the product rule. So far with where we're at in the class, a really strong indication that the product rule is coming up is if you have a function like that, e⁻x in the mix. That's because we don't have a huge catalog of functions just yet. Trigonometry is not a prerequisite to this class, so we're not doing any product rules that involve trigonometry. Also, we don't have logarithms just yet, since the derivatives involving logarithms is in a further section. I believe that's section 3.6. So at the moment, a product rule comes up whenever you see e to the x, essentially. Now we're going to change gears. I don't want to go too far in the notes since quotient rule is just as important and we want to give it its fair share of time. But let's give a good start to the quotient rule. We'll look at some of the problems here, but I don't want to go too far again and do the derivatives. Maybe we'll end on part A there. We'll see where we end up. So first, let's analyze what's going on with the quotient rule. And really a great way to compare the quotient rule is just to restate the product rule. So let's put it up here. The product rule, in essence, says this. You have a function, f of x, multiplying another function, g of x, and we're doing the derivative of that product. And it breaks down to this. F prime of x times g of x plus f of x times g prime of x. So if you're dealing with the product rule, you always have a plus in the middle, and you do this little game where the prime just moves from one function to the other. Now, looking down below, here's how the quotient rule goes. You're using the quotient rule when you're taking a function divided by some other function. So like over here, we call that the first function, and this one the second function. But in this configuration, we'll say we have a top function. The function on top is f of x. Over here, we differentiate it. Over here, we copy it. The bottom function is g of x. This part is being copied. This part is being copied but differentiated. And the thing that's really new is you divide by the function squared. Not its derivative, just the function to power 2. Another thing that's kind of easy to miss about this is if it's a quotient rule, you'll have a minus in the middle. And if it's the product rule, you'll have a plus in the middle. So one of the reasons I put my f prime first is just so that it's indicated in this way. The pattern is extremely similar. Just know that if you're going for product rule, that's the first change. You put a negative there. And the second change is you're still dividing by the function squared. In Leibniz notation, this is what it looks like. You're differentiating the function here, and you're differentiating a function here. So that's the f prime coming down to that location. And this is the g prime coming down to that location. Well, any questions about the format of the quotient rule so far? Okay. Now, the big struggle with the quotient rule is that it's easy to use in a lot of situations where you really didn't actually have to. So just like with the product rule, that's sometimes the most important thing to know when you should use it and when you really ought not to, when there's a much, much faster way. And it's even a bigger deal this time because the formula for the quotient rule is a bigger formula than it is for the product rule. So it means it's going to pay off even more if we pay really close attention to when we're using it appropriately and when we really shouldn't use it. But again, on a real exam, if you used a quotient rule in a problem that you didn't have to, you would still get full credit if you take all of your steps correctly. This is more just indicating faster ways to compute. So you're not always getting bogged down with a quotient rule. So that's the caution here. The quotient rule can be used in a lot of settings, but we want to be efficient with it and only use it when we have to, is the essential essence of that caution there. So this is a situation where the quotient rule should not be used on the left. Sorry, forgot my left hand and right hand. On the right, you should use the quotient rule. And notice that this is extremely confusing on the first look. F of x and g of x almost look like the same function. They're just reciprocals of each other. So it's kind of strange why over here, you can get away with not using the quotient rule. Yet on the right, you must use a quotient rule. I don't have a great second strategy on that one. So here's the difference. On the left-hand side, we do have some algebra that's going to help us out. If your denominator is just one term, the x, you can rewrite this as x divided by x plus 1 divided by x. On the right-hand side, you have a common denominator of x. And so if you're going from the right to the left, you just add across the numerator, x plus 1 over the common denominator of x. But here on the left, that's not easy to differentiate. But on the right, it is. We can simplify x over x to just a 1. 1 over x, our common strategy in section 3.3 is just to bring x up into the numerator. It turns into x power -1. Then that's our f of x function right there by the red dot. When we go to differentiate that thing, we go f prime of x equals, first, that's a constant being added. So that just goes to a 0. We don't even have to write down anything. On this one, it's the power rule. The old exponent is -1. It's now a coefficient. The new exponent is -2. And you don't have to do anything further with that. But if you wanted to, you can make that a -1 divided by x squared. All I did was take the x power -2, threw it down to the denominator to make the exponent positive. So this is a fast derivative, no quotient rule required. It goes completely sideways on the g of x function on the right. The trouble with the g of x over here is that the denominator has 2 terms. There's no way to take x, divide it into both of those terms, and get a simpler function. Not if x plus 1 is in the denominator. So that's really kind of unfortunate. One subtle change like that, and it throws this whole derivative way off. Well, any questions, folks, with the derivative on the left? Or what we're about to do with this one on the right? Okay, well, the g of x is a true quotient rule kind of problem. There's nothing we can do to get out of that. So let's start setting it up. G prime of x, my strategy for this is the same strategy that we used for the product rule. Although that's an important formula, it's more about the format of that formula. First, let's put in the numerator. The numerator, we want 4 parentheses, just like before. So here's 1, 2. Because it's a quotient, we have to put a minus in the middle. Here's 2 more parentheses. Then don't forget, there's a prime right by the red dot. So let's put it on this one. Then over here by the red dot, there's another prime. So another prime on there, down below. So far, this is the product rule, except since we're using a true quotient rule, I put a negative sign in the middle. And we have to go down below and put something to power 2. That's the g of x to power 2 we see up here. So every time I do quotient rule, I'm always going to pretty much just set it up like that, since that's how it all combines together. That's a good way to memorize it as well, so that we can streamline our work. Next, we take the top function, x. That's the one that's in blue here with the color coding. It goes into just 2 slots in the numerator. So that x gets copied in here and here. It goes into those just first positions. Next, x plus 1, it goes into 3 slots. But a good way to think about this is, if you memorize that f of x just goes into here and here, those 2 positions, then it helps your brain remember that g of x is everywhere else. So we'll take x plus 1 and putting it into all the remaining containers. So x plus 1 here, here, where it's being differentiated, and here, where it's being squared. So that's our setup for the quotient rule. We just need to take 2 derivatives, simplify as necessary, and we're home free on that one. Any questions about the setup so far? Okay, well, let's go and work through this one. First, on that right there, we're taking the derivative of x. Derivative of x, just as a variable, is 1. So that means on this step, it's 1 times x plus 1. Over here, we're just copying the negative x, and we can drop the parentheses and go minus x. Derivative on this term is just as before, that factor really. Derivative of that x turns into the 1. Derivative of the constant becomes a 0. So this is just a times 1 in total. And for the denominator, just like what we were doing in sections 3.1, sections 3.2, when we were doing the derivative from scratch using the definition of the derivative, we never actually expanded the denominator. Same idea with the quotient rule. It turns out it's almost in every single situation, better to leave it in that factored form, x plus 1 squared. The best thing that could happen is you might be able to simplify the function a little bit more. But in the worst case, even if you expanded it, it's not giving us any additional benefit. So it's most simplified and most useful in a factored form, x plus 1 squared. In the end of the day, all that means is we leave the denominator just as it is. We might cancel it off after we simplify, but oftentimes it just gets copied down over and over again as we take our steps. This keeps on going, but we can drop the parenthesis on this. 1 times x plus 1 is just x plus 1. Times negative x times 1 just becomes negative x. Denominator is x plus 1 squared. Then we have like terms, x and minus x cancel, and the whole answer to this is 1 over x plus 1 squared. And that's our total derivative on this one. What we did, folks, this is how the quotient rule works. And this is a situation where you definitely want to avoid a quotient rule. Any questions at all working through either example? Okay. Well, like I said, we're not going to try to get really far on the notes and work to the very, very last minute as fast as we can, since it's a good idea to come back to this quotient rule and practice it a little bit more starting fresh after the weekend. But let's do maybe one additional problem. I like this problem right here because if you recall, we've actually differentiated this one before. It was a while ago, but let's take a look at what we had to do in the past. Better extend that session. So I believe this one was done in section 3.1. That already feels like it was a while ago. And let's scroll down here just a touch, or quite a touch, I guess. Wasn't that one? I should have looked. Oh, it was this one. Here's f of x equals 2x plus 1 divided by x plus 3. This is, in fact, the problem that we're working on right now. But what we did here was we calculated the derivative of f at a using the definition of the derivative. So it was the limit as h goes to 0 of that difference quotient. And the algebra on this is really kind of tedious. It's not that the algebra is hard, it's just that there are so many terms, there's extra tedium that causes the difficulty. I actually practice this one so I don't accidentally forget a term when we go to do it in front of the class. Well, after a lot of work, we got something that looked like this. So on our notes, we should get f prime of x equals 5 divided by x plus 3 squared. So let's give it a try. First, it's a true quotient rule because the denominator is 2 terms. I can't just divide x plus 3 into 2x and the 1 and make this a simpler function. However, if it was this, you really should divide your x into both terms because it's way less work to differentiate that function. Analyzed this way, we're going to think of this as having a top function, 2x plus 1, a bottom function, x plus 3, and we can now say dy dx, the derivative. First, here's our placeholders. 2 parentheses, another set of parentheses. Definitely include your prime symbols and mind where they go. Oh, it looks like I did make one mistake. My bad right here. Also, don't do that if you're doing a quotient rule. That should be a minus sign. Sorry for anyone working in Penn today. Let me highlight that one as well. That's always a surprise when you're using the quotient rule as opposed to the product rule. Then, let me grab an actual pen. Our denominator will be something squared. So if you get used to doing this setup every single time you do the quotient rule, then once again, when it comes time to doing this on an exam, this is going to feel pretty natural and streamlined. What we do next is place in our placeholders the top function. Only 2 spots. It'll go here where it's differentiated and over here where it's simply copied in. Memorizing where the top function goes frees up your mind so you don't have to worry too much about x plus 3. It goes everywhere else. It'll be here, here, and here. Notice if we compare what we did in section 3.1, we already have the denominator, x plus 3 squared. It was just an a in this problem. Now we just have to do a couple derivatives. Any questions, folks, with our setup? Okay, going to the next line, usually I just take that and write it in at the bottom since it's not going to change. So x plus 3 squared down below. Over here, we're taking a derivative. Derivative of 2x plus 1 is just a 2, since the power of x is 1. It'll multiply x plus 3 minus 2x plus 1. So these things in the middle, we're just copying until we get over to here, the last factor of the last term. Derivative of x plus 3 is just going to be a 1. So it's a times 1. And I kind of went crazy on that fraction bar. Let's downsize that a bit. And there it is, folks. That's our derivative. Again, we still have to simplify this, cancel the like terms that we can cancel. But if this was a real exam question, say out of 5 points, you've earned 4 points already. The rest of the points is just to simplify it. That'll involve just distributing the 2 through. Because that's times 1, we'll distribute a negative sign through on this one. So we get our new numerator, 2x plus 6, minus 2x, minus 1. Divide by x plus 3 squared. So now after distributing, we have like terms, 2x and negative 2x. Those two cancel off. The numerator is now just an ordinary 5, which is being divided by x plus 3 squared. Double checking the notes. That's exactly what we got here, but it was a painstaking process using the definition of the derivative. This is where our product rule, quotient rule, and all our rules in section 3.3 are starting to really pay off. Every good mathematical theorem we come up against or come up with is just making computation much, much faster. Well, any last questions, folks, to this stage of the notes?
Sorry, I got a question.
Yeah, go ahead.
So if we had to focus on like how to do the definition of the derivative or these quotient rules, it would be smarter to concentrate on the actual like the shortcuts or whatever, right?
Yeah, absolutely. Pretty much problems like these ones are really only going to come up once. They came up once as a quiz problem, and they're going to come up essentially once on exam 2, and then once on the final exam. I guess that's 3 times. It's coming up a few times on the quiz. They'll come up 1 time on an exam. I'm not going to give a nasty problem like this one. It'll probably be more like, say, not that one. Something a little bit more reasonable, like this one, except maybe with a power 2, an x squared instead of an x cubed. So yeah, I'm only going to ask these questions, and you'll know that you're doing something that's a little bit tougher if it says somewhere on the instructions. Oh, let me open up that quiz. That might be a better way to spot it. Sorry, I almost got the answer to that question. So you're doing the longer process if it says this right here, using the definition of the derivative. But for every other problems, it's not going to say those instructions there. And so you really want to focus more on the rules in sections 3.3 and 3.4. That's how we're majorly going to be doing almost all of our derivatives going forward. Well, does that answer your question there, Doug?
Yes, sir.
Awesome. Other questions at the moment? Oh, the times 1. Let me see, Hunter. Oh, it looks like it came from right here by the red dot. So this times 1 was a result of differentiating this x. The derivative of just a variable x turns into a 1. The derivative of the constant plus 3 went to a 0. So that whole thing right here equals 1 in the derivative. Does that make sense for that derivative there, Hunter? Awesome, you bet. Any other last questions, folks, before we call it a day? Okay, well, have a great weekend, folks. If you're working over the weekend, don't hesitate to reach out. I check my email every single day. It's a ritual and a habit, and so I'll definitely get back to you. I usually check my email during the morning hours. But anytime you write out your email is a good time, or anytime you're thinking about writing out an email or hitting the Ask My Instructor button, try to do that anytime a question comes up, and I'll always get to your questions. Even if I have to wait a little while, I'll definitely get to them. But have a great weekend, folks. I'll see you all next Monday.
Thank